There we go. Okay, so my name is Michael Tremmel. I'm a graduate student at the University of Washington, and I'm going to talk about work I've been doing with Fabio Governado and Tom Quinn at UW, as well as Andrew Ponson, who gave a talk earlier today, and Marta Voluntari at IAP. And what this is about is black hole mergers and cosmological simulation. So what I'm showing here is an example cosmological simulation of a galaxy. It's on repeat. These white dots here represent black holes in this galaxy, which also has a black hole at its center. And you can see the variety of different orbits these black holes have within this galaxy. You can see this one right here coming in for a merger, and the black hole will very quickly sink to the center here. What this is meant to illustrate is if you actually resolve the dynamics of the black holes in these simulations, you come up with a variety of different orbits that exist in the same galaxy. All of these black holes were deposited in this galaxy through previous merger events, but what determines whether or not a black hole reaches the center and merges with the main galaxy's host central black hole, it has to do with a lot of the properties of the galaxies and the merger itself. And this is important if we want to use cosmological simulations to predict the merger rate of supermassive black holes. So these are some results. I'll get back to this later, but the black hole merger rate is a function of time and compare self-consistently with the rate of halo mergers as a function of time to really make a connection between black hole merger events and halo merger events in, again, a way that's self-consistent, that naturally samples the properties of those halo mergers without making any explicit assumptions. Now, the main motivation behind this is that gravitational waves have already been detected at the stellar mass level. We heard about that a little bit before. That's really exciting, but it also means that on the horizon are gravitational wave observations of supermassive black hole mergers, right? And so the question for theorists and galaxy evolution people is to understand what are the host galaxies of these merger events? Where do black hole mergers fit into galaxy evolution, and what can this future data tell us about galaxy evolution, and in particular, black hole galaxy coevolution? Now, the problem in cosmological simulations and studying this has historically been the dynamics of black holes. So here you see an example simulation that uses a common approach to black hole dynamics. And here you have two black holes that will, eventually one of them will get teleported into the center of the main galaxy. Not only does that create sort of an explosive accretion event, which affects the physics of the galaxy in a certain way, it also means that you don't really know much about whether or not those black holes really should have merged and when they should have merged in that interaction. And this is the exact model used in the Illustris simulation for black hole dynamics. And up to this point, stuff like this has been relatively necessary evil because cosmological simulations have a naturally lower resolution. But this new set of simulations I'm talking about today, the Romulus simulations, look to make improvements on things such as black hole dynamics. So these simulations, which you can read more about in my 2016 paper and some other papers regarding ChaNGa and the general simulation used. It comes in two flavors, a 25 megaparsec uniform volume simulation, as well as a 10 to the 14 solar mass cluster zoom-in simulation. Both of these are run using ChaNGa, which Andrew talked about earlier today, and they've been run on the Blue Water supercomputer at the University of Illinois. Now, the focus of these simulations is, again, an improvement upon supermassive black hole physics. And what I'll focus on today is the dynamics of black holes. So I showed in my 2015 paper that it's possible to implement a subgrid model that accounts for unresolved dynamical friction that a supermassive black hole should feel in a cosmological simulation so that you get realistic sinking times for those black holes. Right, so this is an example test case where a black hole is in an isolated halo on a 2 kiloparsec orbit, and it evolves through time, realistically sinking in a timescale similar to an analytic solution. Comparison to the advection scheme that you just saw in that video, where the black hole is immediately teleported 2 kiloparsecs to the center. So you lose that delay time. So like I said, I'm not going to talk too much about the rest of the simulation, but there's also a new accretion implementation, as well as black hole seeding that seeds black holes in the first billion years of the universe. You can read more about that or ask me about that after the talk. I will mention real quick that the simulations have been calibrated to fit z=0 relationships, such as the stellar mass-halo mass relation and the black hole mass-stellar mass relationship. And so what's going on here, right, is that because we can follow the dynamics of black holes down to sub-kiloparsec separations, right, because of the high resolution of these simulations, which I should explicitly say is about 250 parsecs, we can, for all these merger events, we can actually confidently say where the black holes are and when do they actually merge into a single black hole. And so now we can actually, for the first time, in a self-consistent way, study the connection between halo mergers, galaxy mergers, and supermassive black hole mergers. And so here's the prediction of the model. In the black line from the Romulus 25 simulation, the rate of black hole mergers across time and the rate of halos merging that have black holes. I make that distinction because we don't assume every halo above a given mass does have a black hole. So this is just merger events that occur that involve two black holes. And you see that across cosmic time, they follow each other pretty well. Although at low redshift, there's evidence for a slightly more halo mergers than black hole mergers. And this can be understood further if we actually trace the black holes backwards in time to look at the delay that each black hole has between merging and when their host halos originally merged together. And you see that, indeed, most black holes do merge relatively quickly, within 1 billion years or 2 billion years of the original merger event that brought them together. But there's a lot of black holes, 20% of those mergers actually occur well after the halo merger rate that spawned them. And what that means, when we're thinking about connecting observations of black hole merger events through LISA and pulsar timing arrays, if you observe a high redshift black hole merger, it's likely very much connected to its halo merger event. The universe is still young, it hasn't had much time to do anything else. But if you observe a lower redshift black hole merger, right, as you get to lower and lower redshift, you're sampling this tail more and more, and so you're more and more likely to get a black hole that's very disconnected from the original merger event. Right? This will help us understand better what host galaxies we would expect to find black hole merger remnants in. Not necessarily newly merged or merging galaxies, right, but relatively relaxed galaxies that are several billion years post-merger event. Now, we can go one step further, right? All this so far has been Romulus 25. And we can look at the relative contribution of field galaxies, which Romulus 25 is sampling. But it's a relatively small volume. It doesn't have large overdense regions. And so we use the cluster zoom-in simulation and take the data set together and look at the relative signal between the two. And you see that the overall merger rate changes very, very little. The overdense regions don't contribute very much at all, maybe a little bit at high redshift. And at first, this might seem surprising, but in fact, it's not surprising at all, because galaxy clusters tend to have much lower merger rates, especially at low redshift. And this is something that's been well known for many years. And so simply here, we're simply showing for the first time that this also implies, very naturally, that you get less supermassive black hole mergers at later times. You're seeing here the fraction of black holes as a function of the black hole merger redshift. You see that for the cluster simulation, you actually get a bit more, you're a little more likely to have black hole mergers early on when your overdense region is still forming and things are merging together. But as you get past redshift of 4, just like the halo merger rate, it declines in halos. Again, something well known. The black hole merger rate declines as well. So you end up getting very little signal from overdense regions. So what this tells us is that the vast majority of a signal we would expect LISA or pulsar timing arrays to receive from massive black hole mergers is due to field galaxies and not clusters. And so, in summary of what I've said, this has been, we're with a model for black hole dynamics that's able to accurately follow the dynamics of black holes in a cosmological context down to very low separations. We're able to make, for the first time, a self-consistent prediction for when and where black hole mergers should take place and how far removed they should be from their host halo merger events that originally brought them together. And we find, again, that the merger rates between black holes and halos follow each other pretty well, but you do get significant delay times, particularly when you're looking at merger rates that occur at lower redshift. They're dominated by very much delayed black hole mergers. And finally, like I just showed, the contribution from clusters from high density regions is very low and almost minimal at all redshifts. Now, some future work that can come from this is looking at dual AGN, right? Because what I've shown here indicates that black hole mergers actually come from black holes that exist in the same galaxy for several 100 million years or maybe even giga years, that indicates that the prevalence of dual AGN might be more than people think. And again, it's the role of cosmological simulations to make those predictions and compare with observations that are sort of just coming out in the last few years of such systems. And this is an example from my paper where I take it, it's actually the same example I showed earlier in the talk, where in each of these cases, the system is a dual AGN, except, of course, these two, which the black holes have already merged. But here we have both black holes are active, both black holes are active, and again, you have two very close black holes that are active. So understanding how these events come into play in galaxy evolution, and in this case, they result in a quenched galaxy, questions like that can be all answered on a more broader scale using simulations like this. So I'll just leave that up, and I'll take your questions. Thank you.
Great questions?
Very nice talk. About the black holes that are delayed, did you find they belongs to particular kind of galaxy, for example, gas-poor galaxy? There is any trend in that?
I haven't looked at specifics other than mass, and the mass of the galaxy seems to be pretty much the same. You're just as likely. I do think that at lower redshift, the mass ratio of the galaxies is lower. I still have to do a little more work to be sure about that. But so part of the reason why you see so many of these delayed events at low redshift is that when you have sort of more massive galaxies that are more likely to go through minor mergers, you get sort of one galaxy gets stripped and deposits the black hole on a much wider orbit that is more long-lived. But yeah, I'm still working out the details on that.
Other questions? All right, let's thank our speaker again.